Hello, this is the first part of the chapter 4.9, and we will talk today about one of the coolest application of the linear algebra, which help us predict similarly unpredictable random or probabilistic events by building the chains of the probabilities. And as you can guess, we will gonna deal with the vectors, which is described by the probabilities or probability vectors, which is a fancy name for a vector which components adds up to 1. For example, it's commonly used in demography to describe the distribution of the population live in the different regions. For example, let's say we take a region, any geographical region will work, and we say that in this region, 60% of the people live in the city and 40% of the people live in the suburbs. We can write it down as the fraction of the total population which lives in the city and in a suburb. So since 60% lives in the city, 0.6 fraction of the total population will be represented as a first component of our probability vector. The second component, 0.4, will represent the fraction of population in the suburbs. And since it's only 2 regions, that's pretty short vectors. And we sometimes call it the distribution of the populations. So there's a lot of different names, but it has to add to 1. And of course, demographers also try to predict, the city planners try to predict what's happened with the population in a year, 2 or 3. And if we have some kind of data which predicts the pattern of movement between the city and the suburbs, we can express this data in this probability matrix P and apply the current trend on the population movement to the population in the year x0. So if x0 is our current vector, we can predict what's happened in the next year or vector x1 by multiply our current distribution of the population to the probability matrix P. And we'll talk about the details of this probability matrix. But then we can calculate 2 years from now using the same matrix, but multiplied by the new vectors found in the previous step. And again, this is what's called recursive models, when we take the numbers from one step and move it to the next one. And when we calculate it 3 years from now, 4 years, any number of k we can make of prediction for the year k+1 using the data from year k and multiplied by the probability stochastic matrix P. And usually this chain of events called a Markov chain. The stochastic matrix is depend on the situation, but it's always based on the data. And usually the more data we put in this matrix, the better is our model. So, but let's just try to make a very simple model of our city and the suburb movement. And again, we're making a lot of assumptions here, obviously not the most realistic model, but we say that there is no influx from outside of our region, that there is no outflux, people don't die, don't disappear. All they do is just moving between the suburbs in the city. And we call our stochastic matrix of the movement between cities and suburb M. I know I introduced P before, now it's M. Not ideal, but this is how the book treats it. And I will try to do my best to explain your book material. Okay, so our movement matrix. We put the movement from the region in the column. So the first column represents the movement from the city, the second column represents the movements from the suburbs. And the rows represent the direction into the region. So the first row represents movement into the city, the second movement into the suburbs. Okay, So let's see what data will tell us. Say we dig through years of worth of data and find that there is a pretty stable movement from the city to the suburbs, and approximately 5% of the population move from the city to the suburbs. So we are then put this 5% or as a fraction 0.05 in the second entry of first column. We're moving from the city, first column, to the suburbs, second row. Okay, and if 5% moved to the city, which means that 95 didn't move anywhere, or they moved within the city. So we put this fraction 0.95 into the first entry of first column. So we're basically moving from city to the city. Oh, it doesn't move anywhere. Okay, so now let's look movement in the opposite direction. Let's say the data tell us that 3% of suburban population moves from the suburbs to the city. And again, we are represented movement from suburbs by the second column. So we have to put our fraction 0.03 in the first entry of the second row. So we're moving basically from suburbs to the city. And okay, since 3% of the population move, 97 does not move anywhere. So we have to put our 0.97 fraction at the intersection of from suburbs to suburbs. Okay, and that's it. So that's enough to actually make predictions for as many years as you want. So we have our stochastic matrix. Let's just try to make some prediction. What's happened in a year? And again, we need to start somewhere. Suppose that in 2014, the population of the region was total 1 million people, and out of this 1 million people, 600,000 lived in the city and 400,000 live in the suburbs. Let's try to make prediction for the next year, year 2015. Again, X0 represent 2015. So 1 year later will be 2015. So all we have to do to take our vector, which represent our current population, multiplied by our stochastic matrix of movement, and we'll get prediction for the next year. So we write down our matrix explicitly, put population in the vector X, and just perform simple matrix calculation and end up with the vector X1, population in 2015, which has two components. First component, 582,000, will represent predicted or projected city population in the year 2015. The second component will have a projection for suburban population in year 2015. And that's actually pretty straightforward applications of linear algebra. However, it's kind of cumbersome. It has all these thousands, which is hard to deal with large numbers with a lot of zeros. So what often demographers do, they perform what's called per capita calculation. We can take our vector X and divide it or normalize it by the total population. And that's give us, that's our original probability vector, X0. So basically we normalize it by the total, and then because we normalize it by total, automatically our probability vector will add to 1, which is pretty cool property. Okay, so now let's try to perform the same calculation, prediction for population in 2015, but now in per capita units. Again, we start with matrix equation, x1 is equal mx0, and we write down explicitly our matrix M, and now our population is as a probability vector or distribution of the population. And again, when we multiply it, our multiplication will be much easier, and we get a vector x1, which consists of two fractions, First of which represent the fraction of the population living in a city. The second is fraction of the population living in the suburbs. And we can go ahead and calculate the prediction for 2 years from now, year 2016, 17, 18, as many as you want. But I would warn you to be very, very carefully with the long-term predictions, because our model is utterly simplistic. Yes, we assume no movement between the geographic region, but we also assume that our movement between city and the suburbs are stable in time, that every years the same fraction of people will move between the suburbs and the city. But things does not stay still. There is a public policy and opportunities, and a lot of different things happens in the city. So this kind of trend might not last long. The geopolitical reasons can move people away to the different regions, or there may be some influx of the, like educated workforce in the city, and it became work more attractive, or maybe the suburbs will have a new industry and the people will moving in. So very careful with the long-term prediction, but short-term predictions works really well. However, there is one long-term tendency of this matrix which can be really useful, and we will talk about it in the part 2 of this series.